This is where experimentation meets accountability. In this section, you'll learn how to use MLflow inside notebooks to track model training as it happens, capturing parameters, metrics, artifacts, and runs so nothing is lost, forgotten, or overwritten. By bringing visibility and structure to your experiments, MLflow turns ad hoc notebook work into repeatable, ready for audit process, helping you understand what worked, compare results over time, and confidently move from experimentation to production-ready models. MLflow is the backbone that brings order, transparency, and confidence to the machine learning lifecycle. And here we see why it matters. As an open source platform, MLflow helps you manage everything from experimentation to deployment, with MLflow tracking as its core. Tracking automatically logs the details that make or break a model, parameters, metrics, and artifacts, so every experiment is recorded, reproducible, and easy to review. Whether you're training models in notebooks or scripts, MLflow gives you a single, consistent way to compare different runs side by side, understand what changed, and clearly identify which model performs best. Instead of guessing or relying on memory, you get a full searchable history of how each model was built and evaluated. Consider a data scientist training several versions of a diabetes risk model, experimenting with different feature sets and algorithms. MLflow tracks each run automatically, logging accuracy and AUC, which is a popular performance metric for binary classification models that measures how well a model can distinguish between two classes. For example, positive versus negative or high risk versus low risk, making it easy to compare results, select the top performing model, and confidently deploy it knowing exactly how it was created. Before you start logging experiments, consider a quick setup check to make sure MLflow is available on the compute you're using, because great experimentation only matters if it can be reliably tracked. The key idea, tracking parameters, metrics, and artifacts, works the same in notebooks and scripts, but the installation and setup differs because the compute differs. Notebooks run on a compute instance where MLflow is already configured in the Azure Machine Learning, while scripts run on compute targets where they must include the MLflow and Azure MLflow packages in your environments, so they're installed before execution. That tiny setup step is what turns I trained something into a repeatable, comparable, and production-ready experimentation workflow. For instance, you train a churn model in a notebook first, MLflow tracking just works, and you log accuracy in artifacts like the trained model file. Then you operationalize that same training as a scheduled script on a compute cluster by adding the MLflow and Azure MLflow to the environment. You get the same run history and metrics tracking, even though the compute is different. Now let's see how MLflow connects your local development work to a centralized enterprise-ready tracking system, even when you're not running on an Azure compute instance. When you're working in notebooks on your local machine, a few deliberate setup steps, installing the MLflow and Azure MLflow packages, retrieving the MLflow tracking URI from the Azure portal, and setting it explicitly in your notebook ensures every experiment you run is logged to the Azure Machine Learning workspace. This single configuration line bridges local experimentation with cloud-based governance, making parameters, metrics, and artifacts immediately visible, searchable, and comparable across the team. It's the difference between isolated experiments on a laptop and a production-grade tracking that supports collaboration and traceability. Consider a data scientist prototype in diabetes risk model locally on a notebook, sets the MLflow tracking URI once, and runs experiments as usual. Each run automatically appears in the Azure Machine Learning, allowing teammates to review metrics and models without needing to access the local environment, turning a quick local testing into fully traceable, searchable research. Tracking model performance in a notebook becomes dramatically easier and far more trustworthy when you standardize your workflow around MLflow experiments. In practice, you'll follow a tight loop. Create an experiment, train a model while logging parameters, metrics, and artifacts, and review and compare runs side by side to determine what actually improved. MLflow gives you two clean paths to do this. Turn on the automatic capture with MLflow Autolog, which is great for quickly collecting common metrics, parameters, and model info, or use explicit logging with MLflow.log functions when you need to record custom metrics like business-weighted error, artifacts like a confusion matrix plot, feature importance chart, or a serialized model, or additional metadata. Best practice is to keep experiments consistent and comparable by using clear experiment names, adding tags for dataset model versions, and logging the same core metric every time, so your winner is based on apples-to-apples evidence, not missing telemetry. When you're ready to train and track models in a notebook, MLflow gives you a clean, repeatable pattern. It creates an experiment to group runs, and then it logs the results as you train, so every iteration is comparable. This slide highlights exactly what workflow is. First, establish a named container for your work. An MLflow experiment then captures what matters during the training using automatic logging and your custom logging. And then in a notebook, creating the experiment is as simple as running the command shown here, mlflow.set experiment, and then we have the heart condition classifier that we can use here. Ensures every run of that notebook is logged under the same MLflow experiment, grouping runs, parameters, metrics, and artifacts, so you can easily compare different model iterations and hyperparameter changes. This part works the same whether you're working with a local compute or a compute instance. The experiment and its tracked runs are recorded the same way, keeping model tracking consistent regardless of the compute environment. Best practice here is to set the experiment name once at the top of the notebook. Keep naming consistent across your team so runs don't scatter across multiple similarly named experiments, and pair MLflow.autolog for fast baseline coverage with custom logging for domain-specific signals. This way your notebook experimentation stays exploratory, but your tracking stays production grade. When you're using a common ML library, MLflow autologging is the fastest way to get reliable experiment traceability with almost no effort. Add 2 lines, import MLflow, and call MLflow.autolog, and MLflow will automatically capture parameters, metrics, and model artifacts without having you to decide or remember what to log each time. Consider this use case. You're iterating on a churn model in the scikit-learn or XGBoost. Autologging will record each run's hyperparameters and performance metrics, plus artifacts like the fitted model, so comparing runs is effortless. Best practice is to enable ml.autolog before you train and still add targeted custom logs for business-critical signals like recall at 5% false positive rate. Autologging is supported for the following libraries: scikit-learn, TensorFlow, XGBoost, LightGBM, Spark, FastAI, and PyTorch. So this pattern scales across your stack with minimal code changes. When built-in autologging isn't enough, custom ML MLflow logging lets you capture exactly what you care about cleanly and consistently inside each experiment run. You could use MLflow.log param to record an input setting, a single key value pair, such as learning rate equals 0.05, or MLflow.log metric to store an outcome you want to compare across runs, a single numeric value, like F1 score equals 0.86, and MLflow.log artifact to attach files that explain why a run performed the way it did, like a saved confusion matrix image, ROC or receiver operating characteristic curve, or a feature importance plot. Save the plot to disk first, then log it. Here's a quick use case. You're tuning a fraud model and want to optimize the business impact, not just AUC or area under the curve. You want to log a custom metric like false positives per 1,000 transactions with the MLflow.log metric and log a threshold analysis chart with MLflow.log artifact so reviewers can verify the trade-off. Best practice, keep parameter and metric names stable across runs so comparisons are apples to apples. Log metrics at the same evaluation point, same data set split and threshold, and always attach at least one diagnostic artifact per run to make results explainable, not just numeric. Here we see how Azure Machine Learning Studio surfaces everything you log during an MLflow run so you can quickly evaluate and understand model performance. In the Run page, log parameters and metrics appear in the Overview and Metrics tabs, giving you a snapshot of values such as accuracy or AUC across runs. Any plots or visualizations you log as artifacts, for example, a ROC curve or a confusion matrix, show up in the Images tab, while additional files such as exported model artifacts or logs are available under Outputs plus Logs. Together, these tabs provide a complete, organized view of each run's configuration, results, and supporting visuals. For example, when training a diabetes classification model, you might log accuracy and AUC as metrics and a ROC curve as an artifact. In the Azure ML Studio, you can immediately open the run, review the metrics in the Metrics tab, and inspect the ROC curve under Images to understand the model's trade-offs. Best practice is to consistently log the same core metrics and key diagnostic artifacts for every run. This ensures that when you compare runs in the Studio interface, you are making reliable apples-to-apples decisions about which model version should move forward. Here we see how to retrieve and analyze MLflow experiment results directly from a notebook connected to an Azure Machine Learning workspace. Instead of only browsing runs in the Studio UI, MLflow lets you query experiments programmatically. For example, MLflow.search experiments returns available experiments, and ML.search runs gives us the ability to retrieve the runs and their logged metrics so that you can compare these dynamically in code. This approach gives you a precise control over which runs, experiments, or subsets of results you analyze, especially useful when a project includes many models or repeated training iterations. For example, a data scientist evaluating several diabetes classification models could programmatically retrieve runs from a specific experiment and immediately compare values like accuracy or AUC across runs in a notebook. Note that you can choose to visualize the retrieved metrics in a notebook by using Python libraries like matplotlib, turning raw metric tables into quick performance charts. Best practice is to filter and analyze runs in code, for example, by experiment tags or metric thresholds, and visualize only the key metrics needed for decision-making. This keeps comparisons reproducible and avoids manually hunting through runs in the UI. Now it's time for our knowledge check. Question 1. You want to train a diabetes classification model with the Scikit-learn library. You want to focus on experimenting with the model and minimize the effort needed to log the model's results. What logging method should you use? Answer: autologging. Question number 2. When you use MLflow tracking, when training a model in a notebook running on Azure Learning Compute, on which tab in the studio can you view the model's result? Answer: Jobs. You've now seen how MLflow transforms experimentation into something reliable, explainable, and ready to stand up to real-world scrutiny by tracking parameters, metrics, artifacts, and runs, whether you're working locally in notebooks or at scale on Azure Compute. You turn trial and error into transparent, repeatable engineering discipline. This is the bridge from trying models to trusting models, knowing exactly what changed, why performance improved, and how a model earned its place moving forward. With MLflow, your experiments don't disappear, they compound. And that foundation is what enables the next stage of the life cycle. Operationalizing models with confidence through deployment, monitoring, and continuous improvement in a true MLOps workflow. Thank you for joining this session. To continue your learning, watch other videos in this course or explore more on Microsoft Learn at aka.ms/learn.